to learn it today. In order to really make the point, though, let's start concrete. Okay, this can be kind of abstract, and it has 1,000 layers to it. We'll cover a little bit of the layers today. So imagine you're at a light, and the light turns green. Your velocity over 6 seconds is given by a rather clean function. Velocity is t squared in feet per second over 0 to 6 seconds. Say you wanted to figure out how far you went in those 6 seconds, right? Now, it's complicated because it's not an algebra problem where its rate, or our rate, is the same all the time. The rate is constantly building up, and so it makes it hard to figure out how far you went. Let's consider this visually here. If you were to graph velocity over time, 1, 2, 3, 4, I need to calibrate this board again. Sorry, this is going to make me crazy. If you draw a really stretched out wide graph and choose a fairly small vertical scale so you can get the whole curve on, and it might look something like this. 1, 2, 3, 5, 6. That's time in seconds. And we're going to need to go up to a velocity of 36 by the end, right? Right. So let's go something like 10, 20, 30, and 40 is up there too. The curve then would look something like 0, 1, 4, 9, 16, 25, and 36. Like that. Yeah? In essence, a parabola, but again, my scale is making it look like it's still going. But it's important in order to draw rectangles here. All right. Now, we're going to make a connection between the analytical and the visual here. We want to estimate how far we're going to go. And we're going to do that by breaking it up into 6 1-second chunks. How far did I go about in the first second? How far did I go about in the second second? Now again, it's going to be about because the rate is constantly changing. The rate's not always the same for that 1 second. It was going from 0 feet per second to 1 feet per second, so I can't really say exactly. But say we wanted to be conservative. If we wanted to be conservative and estimate how far we went in this first second, I could use the lowest possible velocity in that time frame. So to find out how far you went in the first second, I could say from 1 second, from 0 to 1 seconds, which is 1 second, I will use the velocity at time 0. Because I know that the velocity is actually that and more, and that would then be a conservative estimate. That would pretty much be saying that in that first second, I didn't really go at all, which I know I did, but again, we're being conservative. In the second interval, which is from 2 seconds to 1 second to 2 seconds, which again, I know is a 1 second interval. I'm trying to show where the numbers come from. I could then say, all right, at the very minimum in that time frame, I could use a minimum velocity of the velocity at time 1. In the next time frame from 3 to 2 seconds, I could use the least velocity or the lower velocity of 2 seconds. From 3 to 4, which would be a 1 second interval, I could use a conservative estimate of the velocity at 3. From 4 to 5, which is a 1 second interval, I could use the velocity at 4. And from 5 to 6, I could use the velocity at 5. Again, then I would get an overall pretty conservative estimate. Now look at the units here. In each case, I'm taking 1 second times velocity in feet per second, so I'm getting feet, or displacement. Each of these represents an area. every one of these calculations corresponds to one of these rectangles. This first calculation represents the base of 1 second times the velocity of 0 seconds. This calculation is a base of 1 second times the velocity at 1 second. So it's the connection between the visual, the area of those rectangles really represents a rate times time or a displacement over a time interval. Area equals displacement. Are you with me? Okay. If I calculate them, I get 1 times, what is the velocity at time 0? 0. Then 1 second times the velocity at time 1. Remember, the velocity is t squared. So the velocity is, f1 is 1. The velocity at time 2 is 4. The velocity at times 3 is 9. The velocity at time 4 is 16. And the velocity at time 5 is 25. Okay? So, this would then be 0 plus 1. Pause. What is that 1 set? What does that 1 represent? What is it? That 1 represents an estimate of how far you went in or between 1 second and 2. Okay? That is a displacement or distance because it's moving forward. It's the goal. Right? That next one, 4, that's 4 feet. That's, say, ballpark in that third second, or from 2 seconds to 3 seconds, you went about 4 feet in that time interval. Then you're going a little faster. And in that next second, you went about 9 feet. And then you're going a little faster. The next second, you went about 16 feet. And then the last, you're starting to really travel far in 1 second, so you're going 25 feet. Overall, then, what do we got there? 41, 50, 54, 55 feet. You track it? Okay. Would you then try being a little less conservative? Go an overestimate. We were going an underestimate here because I know from time 0 to time 1 the velocity is actually bigger than the velocity at time 0. We use velocity at time 0 to get a conservative estimate. If we wanted a little more generous estimate, we could, I'll get you started, I could say in that first second, I could use the velocity at the right endpoint or the velocity at 1. Would you crank out the more liberal estimate or the upper bound with 6 second intervals? Start to see a pattern. What'd you get? You got 91 also. Okay. Now, that we just did then in terms of areas here, we used the right edge each time. Now, really, that then is overestimating the true distance, so displacement. So I know that the true displacement on 0 to 6 is somewhere between the overestimate of 91 and above the lower estimate of 55 feet. Somewhere in between. Okay? Are you with me? All right then. Let's try then to get better. Now we could do, instead of 1 second intervals, I could do half-second intervals or 10-second intervals. Or we could work with infinitely many intervals. Now that, to me, is pretty cool. Imagine the idea here of you're taking the intervals down to 0. And it feels like rectangles with zero base should result in zero area. And yet, while the base of each rectangle is going to zero, the number of rectangles is going to infinity. And so the play between those two will give you the perfect area. That, to me, is one of the beautiful ideas of calculus. The play between infinitely small and infinitely many. So say we took this to the extreme, and instead of dividing this into 6 chunks, I am going to divide it into n intervals. Each time interval then, would be the total time of 6 seconds divided into n chunks. Okay? So each interval is going to be 6 divided by n chunks. Let's say then I call this my first subinterval. Now, I don't really know what n is, so I'm going to call that just 6 over n. This then would be, if that's 1 6 over n, then this would be 2 6 over n's. And this would be 3 6 over n's and 4 6 over n's. Doing that some number of times until I got to the last one. Now, how many rectangles are there? N. So the last one would be the n 6 over n, which is just 6. So it's all good. All right. Now, let's say we use right-hand rectangles. Then each time I calculate area, I am going to be taking a base times height, and I'm going to add all of them. Yeah. Each base is what? What's the base of each rectangle? How wide is each rectangle? 6 over it. The delta x. Delta x is 6 over n. Okay. Now each height, here's height 1. It's the function, whatever I get when I put 6 over n into the function, right? Now the function is actually the velocity. So I'm going to call it the velocity at 6 over n. Height 2, isn't it going to be the velocity at this x? So it's going to be the velocity at 2 6 over n. And height 3 is the velocity at 3 6 over n seconds, whatever that is. And so generally speaking, the height is the velocity at some multiple of 6 over n, counting up by 1 each time. So we're going to use summation notation and call that counter I. Right? I starts, because we're using right-hand rectangles, our first height was when we use an I of 1. And the last height would be here. The nth height is the height, or the velocity at the nth 6 over n, which is 6. So it's going to end at n. Okay. What does each of these, this is totally abstract and extreme. It's crucial that you keep in mind what the heck you're doing all this time. And it's not just going to regress down to symbol pushing. Okay? It needs to have meaning. What does each of these mean? Each time you do this, you're finding what visually? An area of a rectangle. And what does that area mean in terms of the car? It's the displacement, okay? It's a time times a velocity. It's a distance you traveled in that time interval, or displacement over that time interval. You follow? This then is summing all these little calculations of, all right, you're going this fast for 1 millisecond. How far did you go? Then you're going this fast for this next millisecond. How did you go? It's summing those. Now, if I then go a little more precise, the velocity in this case was t squared, or the function squared, or whatever squared. Now, the whatever I'm putting into the velocity is that. So I over 6 in quantity squared. In this case, the velocity was t squared. Cool? If I clean this up, this is eventually 6 cubed over n cubed and I squared. Sorry about that's just terrible. I just kind of simplified the expression. You with me? Okay, now here's where we say, all right, this stuff is going to be the same every time. So I could actually put this out front. It's not counting up or changing with the summation. I could just put this out front and say, all right, what happens when you add 1 squared plus 2 squared plus 3 squared until you get to the end point, n squared? What does that equal? That's what that summation, actually, I didn't mean to circle that. That's what that means. Oh man, I don't know. How do I find what that equals? Well, there's a formula for it. 6 cubed over n cubed. The formula for that, which I don't expect you to have memorized, is that regardless of what you ended at, you could always find the sum of all those squares by that formula. All right? Now we could clean that up, and that would be the area using any number of n rectangles, also known as a Riemann sum. Okay? Now we want to get perfect areas, so we're going to take the area formula to, or the number of rectangles to infinity. If I take the number of rectangles to infinity, then let's clean this up a little. I can divide a 6 out, wouldn't you say? And I could at least divide an n out. And so let's go with the cleaner version of 36, n plus 1, 2n plus 1, those quantities are that product over n squared. Sorry, I blanked out there. Sorry, so what about that limit there? As n gets infinitely large, it's really about the biggest, n squared over n squared. So what's the, if I were to distribute out, what would the n squared coefficient be? 36 times 2, don't forget that 2 over there. So 72n squared over n squared. The little stuff would be less and less important as n got infinitely large, so it would approach 72. Now that is exactly how far it went. 72 feet, exactly. Were we in the right region? Well, yeah, I mean, 72 is between 55 and 91. It's above the lower limit and below the up. Now, that then is the tedious. I think you'll agree. And yet you will have to be able to do this infinite rectangle thing on a quiz on Friday. So I hope you're getting good at it. I'll come back to that. Let's talk about a better way. Almost all the achievements of mankind came from somebody saying, man, there's got to be a better way. It's right. It was there the whole time. It was there yesterday. Yeah, it was. I just put it up there this morning, but whatever. All right. I'll explain later. I'm just about to get to the good stuff, man. Don't wander. All right? Here. Now, like I said, there's got to be a better way. We've got to have a better way. I just determined that if the car has a velocity of t squared for 0 to 6 seconds, it travels 72 feet. Boom. You follow? The better way. If it traveled 72 feet, doesn't that mean it changed position from time 0 to time 6 by 72 feet? All right, then. Well, let's go there. Instead of doing all this rectangle stuff, let's go at a totally different angle here. What's the velocity's position relationship? Now, let's talk position then. If I could get at this by using position, well, let's get position. What's the velocity relationship to position? Velocity is the derivative of position, right? All right, now, that's great, but I don't have position to take the derivative of. I have velocity. So if I were to look at this a slightly different way, what if I wanted s? Well, Well, I would want to get rid of the derivative. How do you get rid of a derivative? An antiderivative. I could take the antiderivative of both sides and get the velocity. So let's, or the position, excuse me, not the velocity. Okay? So let's take the antiderivative of velocity. We've been doing that. What's the antiderivative of t squared? Raise the power by 1, divide by the new. 1/3 t cubed plus a constant. Okay, now I haven't gone back to this enough. My bad. But finding that constant, you need an initial condition or an initial condition. Let's say at time 0. Now this is actually relative to what I call position. But let's say at the light, that's position 0 on a number line. All right? At time equals 0, s equals 0. I'm going to refer to that as my starting position. So if I plug that in, I get 0 equals 1/3 t cubed, or 0 cubed plus c, which implies that c in this case is just 0. So my function, my position function is s of t equals 1/3 t cubed. That finds position at any time. Cool? All right. Now, I have the position function. I could therefore find how much did my position change over the interval by just saying what is position at time 6, take away where I was at time 0. Well, at time 6, that would be 1/3 6 cubed, and time 0 is just 1/3 of 0 cubed. Well, that would just be then how far I went from position 0 to where I was at time 6. What's 6 cubed? 216 divided by 3? 72 feet. Now, I think you'll agree that that's a heck of a lot easier than an infinite rectangle. So let's sum up what the heck, what did we just do there? We really did two things. What's the first that we wanted to find change in position? So the first thing we did was get position by integration, anti-differentiation, okay? So we need to take the antiderivative, get position, and then after that we had position, then I went to this step and I found the difference in the two positions at the end point and the starting point. And I took the difference in the position at the end and start at the time interval. Now the notation for this would be something like this. Let's look at this here. We started off with the area of infinitely many rectangles. And we did that by taking the infinite limit of the summation from 1 to n of delta, it was really delta t in this case, times velocity at different times, yeah? Now, all that was the infinite stuff. But what we did here in calculus writing would be to say we took the antiderivative, which we use that symbol. Now up to this point, that symbol was just okay what that symbol is. But now I want you to see this as an S. It's an S. It stands for sum. Okay, that's a Greek S. I know it looks like an E. It's not an E. It's an S. Sigma is an S. That's a Greek S. This is a Roman S. Okay. The sum of the antiderivative, so we took the antiderivative. When we said change in position, we found the antiderivative and took it at the end point minus the starting point. You follow? Now, in terms of notation here, those go here. We didn't just take the antiderivative. We took the antiderivative and then took the difference from 0 to 6, or took it from 0 to 6. Now this is called a definite integral. When you have an antiderivative with limits to say over this time interval, definite integral. That just blew the world away about 400 years ago, and it just changed all of science, engineering, and mathematics. You don't even, we're not even there yet, oh my goodness, okay? But in terms of congruence between these two here, if I look at delta t infinitesimally small, it starts to approach the velocity at different times is there. And this whole sum, that's that integral, the infinite sum of infinitely many rate times time calculations, all those. All right, now I use velocity here because people understand car movement and it makes sense, but this doesn't have to be limited to just velocity. On a much bigger scale, the fundamental theorem of calculus applies to any function. And depending on your textbook, this is written one of two ways. I'm giving you both because I want you to be familiar with both, all right? If you want to find the area between a curve, f of x, and the x-axis on some interval a to b, and that area can have a lot of meanings, okay? Depending on the problem, it has lots of meanings. But if you want generally to find the area under a curve, you can write a definite integral, and to evaluate the definite integral, you take the antiderivative. Capital F is the antiderivative of whatever's in the integral. Okay, you take the antiderivative and then evaluate at the upper limit minus the lower limit. Okay? That process then is bypassing all that infinite rectangle sum and getting straight to the perfect area via calculus instead of geometry. So you take the antiderivative, evaluate at the upper minus the lower. This is if you think about the curve. I honestly try to understand myself because this could blow your mind. I could just think about this all my life long. This is nuts. If I took the area under little f of x, this area here, if I divided that up into squares, it would be the same as if I graphed the antiderivative, capital F, and looked at how high I went between those two y values. That area represents that distance. That's crazy to me. That's a two-dimensional corresponds to a linear measurement. That's nuts. Depending on how you look at the original curve, this is another way to look at it. Say you imagine that instead of calling the original curve you were finding the area under f, say you thought of that as a derivative. Okay? Then in that case, the area under that curve would be the antiderivative is a little cleaner. What's the antiderivative of f prime? Well, it's just f at upper minus lower. And so that would represent the linear distance between f over f from b to a. We'll do some symbol pushing today, but this has amazing real-life applications in a lot of ways that we will get to all year. So cool. So let's try doing one in what you're going to see on the homework tonight. So you have this definite interval, and they'll say evaluate. Okay? Now in my mind, at the very back of my mind, I'm still thinking, okay, that's an area under the curve. Okay? But let's do that without all the graphing and all the rectangles. We're just going to do it in a two-step process. Take the antiderivative, upper minus lower. So what is the antiderivative of x squared? 1/3 x cubed, and the antiderivative of 2. 2x. Okay, now when you do a definite integral, you typically show the antiderivative, and then you say, hey, I'm going to evaluate this in a minute. But you're showing the person, hey, this is what my antiderivative is, check that first, and now we're going to go on. That's the first step. Now we're going to evaluate, oh, sorry, now you probably thought, well, what about the C? Okay, so I'm going to put that in there. And honors people, just stick with me. You'll see, okay? The plus C, cool? Now, my idea then, or the idea is that you, not my idea, I wish it was, you evaluate that antiderivative at the upper limit, this one. So if I plug 4 into that, I get 64 thirds minus 8 plus C. Notice the heavy use of parentheses. It's crucial that you enclose. Now I subtract that function evaluated at 2, which would be 8 thirds minus 4 plus C. Now, please don't worry about simplifying inside these parentheses, inside those parentheses. It's much cleaner and easier if you look at these two, and these two, because they're like terms. They both came from the kind of same place. They both of these guys came from this cube. So they'll always have a common denominator. 64 thirds minus 8 thirds is 56 thirds. Negative 8 minus negative 4. Negative 4. And C minus C goes away. Now, that will always happen. The C's will always subtract away. And so because of that, when you do a definite integral, you won't even show the C, because that would always happen. It's just a waste of time. You know, we all know it, but it's going to always go away. So in a definite integral, we don't write plus C. We just finished. What's 56 thirds minus 4? There's going to be some arithmetic you're going to have to do. There's going to be fraction heavy problems. I hope to goodness sake that you can do fractions, because you're going to do a lot. 44 thirds. Okay. Now, we just calculated area under that parabola curve between 2 and 4, but we didn't even look at the visual. The plus C goes away every time. So on indefinite integrals, let's just be clear. Indefinite integral is just an antiderivative problem. It's when I give you this and I just say, do it. What do you do? You just take the antiderivative and you say, all right, the original function could have had a constant there that went away when I took the derivative. That's an indefinite integral. When you do an indefinite integral, you should have the plus C, because you don't know what happened to it when you took the derivative, so it needs to be there. But on a definite integral, that'll look like this. You'll say e to the x dx from 0 to 1. You take the antiderivative and say, forget the plus C, it goes away anyway because it subtracts away, and you just write the antiderivative at that other number. All right? Try these two, please. Two-step deal. Upper antiderivative, and then an upper minus 1. Cosine of x or negative cosine of x? Negative cosine. The upper minus the lower. That's crucial that you get the order right. Done with the first one? What'd you get? 2. Tell me graphically why that makes sense. Or at least the sign makes sense. What did I just find visually? The area under the sine curve from 0 to pi is about, not about, it is 2 units. Now, let me explain at the very least why it's got to be in the right ballpark. What's the, say I estimated it with this rectangle. What's the base of that rectangle? Pi. What's the height of that rectangle? What's the area of that rectangle? Pi. Is that rectangle a little too big though for the area? Yeah. So the area of 2 being 2 less than pi, it's at the very least in the right ballpark. Okay. Try this one. It's the antiderivative of e to the x plus 2. E to the x plus 2x. Evaluated at 2, I would have e squared plus 4. And evaluated at 0, I'd have e to the 0 plus 0. It is so common that people think when they have a 0 that, oh, this will be nothing, I'll just take a little shortcut and say ignore that. Does this come out to be nothing? It does not. E to the 0 is something. All right? So don't assume that something to the 0 is nothing. It sometimes is. It often is. It frequently is. It almost always is, but not always. E squared plus 4 minus 1. You get e squared plus 3. Pause for a second. Did anybody feel tempted to pick up their calculator? Say, what is that? E squared plus 3. Now, if you said yes, then you are really ticking me off, okay? I don't understand that. I know you think the calculator has magical powers, but this, exact or estimate? Exact. Pick up your calculator. What are you going to get? Exact or estimate? Estimate. So let me understand this. You're going to do more work for a less exact answer? Why would you do that? That's good. Leave it alone. Leave your freaking calculator on the desk. That's perfect. Don't mess it up. Okay? All right. I kind of touched on this already, so I'm just going to get started on this to talk to my point, and then we'll bail it halfway through. So in a definite integral, I anti-differentiate. What's the antiderivative here, my friend? 1/3 x cubed plus x squared minus 4x from 1 to 3. When you evaluate it, it would be something like 27/3 plus 9 minus 12 minus 1/3 plus 1 minus 4. You will find as these get harder and harder that you'll be so much better off if rather than simplify completely inside the fractions, you keep common denominators in mind. These are common. You might use them. You'll find the problems easier if you do. These guys are whole, so you could probably combine those and that's not an issue. But use the common denominators you'll get, and it'll be easier. Would you try the last one, please? Sketch and sketch the graph of what you're finding, then evaluate the integral. about some answers and how it's okay. How's it going? Are you getting something like -4/3 eventually? Should I shut up and give you a second to finish? Go ahead, you can say it. Yeah, shut up. The point I want to make is about the thing. Okay? It kooks people out. I'm grateful that you think of this as area because I taught you that way and I want you to, but it kooks people out to see a negative area. It makes sense to get a negative area because if I looked at each of these rectangles, if I had done this in a finite fashion, this delta x times a height that area is coming from, well, delta x is always positive because I always go left to right. But what are the function values here in this region? What are the y values? They're negative. Y is negative here. So negative area is to be expected. So -4/3 is going to happen. Now, that doesn't mean you say, okay, forget that, I'm going to call it 4. You leave it -4/3. And the reason is because depending on the application, negative might be good. You might want to know the negative. For example, if this is a movement problem, that might indicate you went backwards, and you want to know that. Or you went down if it's vertical movement, and you want to know that. Or generally something decreased by that much, and that's important. Other times, when I say find the geometric area surrounded by, well, then you want it to be positive, and you'll make it positive. But for now, negative is okay for some problems. Okay, so don't kook out if you get a negative. It's all good. All right. We turned in 43 yesterday, yes? So we need to turn in 44 today. Tomorrow's lesson is short, so tomorrow is the day I'm thinking about going over the test. Although, again, the offer is there. If you want to see your test, come talk to me after class or 7th period or after school, and I can show you. Okay, 44 questions. Questions on 44. 44 questions for me. 44 questions for me. Do you have any 44 questions on to me? No? Moving on to 45 then?
No.
Oh. Tranquilo. Oh, I like that. Is that like Spanish for chill? Yeah. Chill out. Tranquilo. I'm going to say that. All right. Questions on set 44? All of them. That's rough. I should probably see you in 7th hour. 20. Did you do 24 and 44? Oh, that's too bad. That's a good problem. That's really good. Should we talk there? Start there first then?
And also too.
24 and 2. Boom.
It's not.
Oh man, okay, sorry.
It takes me 8 minutes to light a candle.
Okay. You can call this, subtitle this, math is everywhere, you just don't see it. When you turn the oven on, this is how I actually live my life. I think about these things, and these are actually true. When you turn the oven on, it's not just a magical oven, it's a mathy oven. Okay? It starts probably at room temperature, or ballpark, depending on how well insulated, but it's probably about the room temperature, which means this is probably erroneous. It should probably be something plus the room temperature. But the oven constantly heats up until it gets to the temperature you request. Okay? At that point then, it doesn't constantly keep a measure of heat to keep the temperature right there. It turns on and off. Depending on the quality of the oven, more often on and off. But it stops heating and then it just sits there and lets the temperature do its thing. And the temperature in the oven will gradually then start to fall until it falls too low and the oven says, okay, I need to kick it up so it's closer to 300. And it turns on and it'll actually heat it past 300 and then it'll kick off again. And then it'll start to fall until again it says, oh, too low, and kicks on. And so the temperature of an oven actually would be modeled by something like that, where you are constantly growing until you get to the desired temperature, and then it has a sinusoid kind of periodic wave after that. Now surely this must be continuous, because it's not going to go from one temperature straight to the other without everything in between. That's the intermediate value there. So it is going to be continuous. Question though is it differentiable? Well, we want to make it continuous. The oven is preheating over the first 10 minutes, then it kicks on periodically to keep the temperature around 300 degrees. In order to make it continuous, I need these two branches to meet, yeah? So we would say something like the limit as time approaches 10 from the left needs to equal the limit as time approaches 10 from the right. 10 from the left, what's 10 from the left? 300. And it needs to equal 10 from the right, which we don't know k, so it's going to stay k. K plus 10 cosine of pi 10 minus 10, or 0. Now that means then that 300 is k plus, what is 10 cosine of 0? 10, so k is 290 in order to keep it continuous. All right, make sure I get 44 by the end of the day. I look forward to Sunday seeing some 8 people in for questions instead of just those PC turkeys. You guys don't come in a lot for help instead of that. Uh-huh. Yes, I'm with you. Yes, if it's a constant, that's exactly right. It's a mixture of infinite rectangles and redemption quiz for test correction. Redemption. Sometimes